Conversions are very important, and they can be made difficult or easy depending on how you do it. But one of the easiest ways to carry out a conversion is with what's called the factor label methods. What we do is we use equivalents, that means conversion factors, to bridge between units that you have and the units that you want. Throughout, we cancel units through the conversions to yield the desired unit and to check our work and to make sure that we've applied the conversion factors correctly. Some examples, well, how many tons are there in a megagram? And what are the English and Celsius equivalents of 293 degrees Kelvin? So these are the types of questions that you might need to solve using the factor label method. Things like this. 3.5 miles, how many feet is that? If we have 10.39 square miles, how many feet squared is that? If we have 6,651 acres, how many square miles is that? If we have 0.625 gallons, how many cubic feet is that? Here's another question. If we have 0.5 inches, a half an inch of rainfall on a 0.85 mile squared area, what is the volume of rainfall that fell in cubic feet? Believe it or not, this is an important question to be able to answer. Also, an acre-foot of water is the volume of water needed to cover 1 acre to a depth of 1 foot. This we covered under units, and the question is, how many gallons is this? And why might you want to know this? You might want to know this because you might want to know how many households 1 acre-foot can sustain over the course of 1 year. And here's a word problem, and it's a common word problem. The average amount of evapotranspiration at Beowawe, which is, again, evapotranspiration is water vapor being transferred to the atmosphere by evaporation and plant activity, is over 50 inches. It's 51.17 inches per year. So the question is, how many acre-feet of water are evapotranspirated at Beowawe on the average every year from a 10-mile squared area? Now, why might you want to know a thing like that? You might want to know that because you might be planning to bring water to a 10 square mile area to grow something. And you might want to know exactly how much water you have to deliver in order to just keep even with the amount that's transferred back to the atmosphere by evapotranspiration. The factor label method is pretty easy. And again, one of the strengths of the factor label method is that it's used to help you organize and keep track of the conversions that you're doing, especially when you're doing them over several steps. It's used to convert between different units when the problem is a little bit more complicated than the ones that we just saw. So the first step is to really set up a factor label equation. We take a quantity, what we're given, we take a conversion factor, and then we multiply or divide by that conversion factor to get our desired units. The second step is to cancel units as necessary to make sure that the conversion that we just carried out actually produces the result that we want. And then third, using the numbers, we calculate the answer. Remember, it's very important to understand one thing. There may be several conversion factors used in one factor label equation. Here are some of the conversion factors that are pretty common. For example, 1 meter equals 3.28 feet. 1 meter equals 39.4 inches. 1 inch equals 2.54 centimeters. If we're going from meters to feet, then the way we might array this in something that looks like a fraction that we can use in the factor label method is that 1 meter on the top is equivalent to 3.28 feet on the bottom. Or, if we happen to be going from, this is if we're going from feet to meters, if we happen to be going from meters to feet, we invert it so that meters are on the bottom and feet are on the top. And the same is true with the rest of the conversion factors. Let's try this example. Acre-feet to liters. Liters are a volume, a measure of volume, an expression of volume in the metric system, and acre-feet is an expression of volume in the English system. So how do we do this? First, we set up the conversion. We have 2 acre-feet. You see it there on the left-hand side. We know that 1 acre-foot is the equivalent of 43,650 cubic feet of water. We can find that online using conversion websites such as convertit.com. We can then go from feet cubed to inches cubed, 1 foot cubed is equal to 1,728 cubic inches of water. And then we can go from cubic inches to liters. Now we could actually skip the step of going from feet cubed to inches cubed and just go from feet cubed to liters. But in this case, just to add one extra conversion factor and to show how these are arrayed, then I've added the inches cubed step as well. Okay, and we can see that each conversion factor has a conversion amount with it. Again, 1,728 cubic inches is the equivalent of 1 cubic foot. So there are 3 conversion factors in this equation. In this case, what happens is that we have acre feet on the extreme left and acre feet on the bottom. So acre feet cancels acre feet. We have feet cubed on the top here and feet cubed on the bottom here. So feet cubed cancels feet cubed. We have inches cubed and inches cubed, and they cancel as well. And after the cancellations, top and bottom, are completed, you can see that on the bottom here, units stripped away, all we have left on the left-hand side is liters. After that, it's simply multiplication and division. So 2 times 43,650 times 1,728, and that quantity divided by 61.02 is going to be equal to 2,472,212.39 liters. Now, significant figures are important. Remember, the absolute precision represents the measurement capabilities of a specific instrument. So, for example, the absolute precision of most car odometers is 1/10 of a mile. It doesn't measure less than 1/10 of a mile. It can only measure distances of at least 1/10 of a mile. The relative precision then applies to combinations of basic measurements that have different levels of absolute precision, and I'll show an example of that. Scientific notation helps to determine the absolute precision of a given quantity. Here's an example. If we express 43,200 in scientific notation, it becomes 4.32 times 10 to the 4th. So if this is in kilometers squared, then we really only have 3 significant figures, the 4.32. The rest are zeros. So the absolute precision of this measurement is about 100 kilometers squared. Here are rules for expression of combined basic measurements. When we have multiplication and division, the result has the same number of significant figures as the least relatively precise number. So the least relatively precise number governs the amount of information that we include in significant figures from multiplication and division. In addition and subtraction, the result has the same number of significant figures as the number with the fewest decimal places. Remember one thing. Significant figures means rounding. We have to round when we have significant figures. And so rounding, though, is only done after all the calculations have been made. So if we need to round, if we have to do some rounding at the end of our calculation, we wait. We don't do it in the intermediate steps. We do it after all the multiplication, division, addition, subtraction, and any other options or operations have been carried out. So let's look at this example. Let's estimate the volume in cubic meters of precipitation received in an area. And remember from the previous slideshow that area and volume are derived measurements. In this case, we have an area of 43,000 kilometers squared. The precipitation amount that we've received is 13.1 millimeters. And this is a common way of expressing the amount of precipitation that's received at a point. It's a depth. So now we have, as you can see, a depth times an area. So what is the total volume of precipitation in meters cubed? Well, first thing we have to do is convert the measurements to units needed. We can see first that the 13.1 millimeters becomes 1.31 times 10 to the minus 2 meters. That's the depth now of rainfall on the landscape. And the number of significant figures for that is 3 significant figures. And if we look at the area, it's 4.3 times 10 to the 10th meters squared. That has 2 significant figures. What this tells us then is that our answer, when we're finished, after we're done rounding, will have only two significant figures because the number of significant figures included reflects the least number of significant figures in what we use to develop or to calculate the answer. So this step 2 then is to identify the measurement with the least absolute precision, and that is the one on the right hand side, which has only two significant figures. Now we carry out the multiplication. Our result is 5.6330 times 10 to the 8th meters cubed. More information than the absolute precision of our numbers actually justifies. So we're going to round according to the number of appropriate significant figures, which is 2, which means that our result, our initial result of 5.6330 times 10 to the 8th becomes 5.6 times 10 to the 8th meters cubed.